Here, this is COMSC 122, and we're down to files and databases. So let me bring in the Colab notebook for that chapter, which is here. All right. So I can run that. Good. All right. Looks okay. All right. So, all right, and I'm going to download. Now this is where it downloads some files. And here, I thought this was actually kind of interesting. It's downloaded something called photos.zip. And you can see that if you click this button in Colab. You can see I now have a thing called photos.zip. And it looks like it has some stuff I created when I ran this earlier. So this is going to remove the old stuff. Okay. And so now if I... Yep, photos is now gone. This is going to unzip photos.zip. And that's going to create a directory called photos. So if I click away and come back, now I have a folder called photos full of those more folders that contain those files. All right, so this is a little bit helpful since we're talking about files and folders to show what you've got. And this is all stored in the container, the Linux container that Google Colab gave me for free here that we're using. So now I have just a directory called photos with some subdirectories containing various things in there. All right, so all right, now they talk about this. Most programs are ephemeral. They run, they produce output, but they don't store anything that remembers for later. If they want to do that, they'd have to store it in a file somewhere. You can just write to a text file, or you can write to a database, which is just a more full-featured place to store information. So first you got to understand file names and paths. And one thing, I thought this was rather strange. There is a function called os.getCurrentWorkingDirectory, and I'm just going to add something here that prints that before they do anything weird. So if I print os.getCurrentWorkingDirectory here, then I get the real working directory. Oh, I see. Thought I got it before. I wonder if I need to do this. There. Then, but it didn't print anything up there. Okay, anyway, at one time I actually got the real working directory, which is, of course, something else inside this container, not Dinsdale. In this book, in this list of code, they have this fake one to return this fake directory of home Dinsdale. Let me see if I can figure out how to get this thing to print. Wow. Oh, that's because this definition was made. Okay. I don't know how to reverse a definition. All right. That's why this happened. This definition had already been made. I thought I'd set this notebook to be regenerated. Anyway, originally you got the real working directory of this folder, and then they change it to this fake one that returns this fake directory, which somehow is useful for the demonstrations they're performing. I think it would be better to have stuck with the real directory. Anyway, so now you get this fake location, home Dinsdale, which would be the home directory of someone named Dinsdale on a Linux system. All right, so now a path, this is called a path, a folder and perhaps another folder or file inside it. Now, a file name is also a path, but it's a relative path because it's just a file name and it doesn't specify what directory it's in. So it'll be in whatever your current working directory is. Now, you can also have a full path, which starts with a slash in a Linux or Unix system. Slash is the root of the whole system, so anything that starts with slash and then continues is an absolute path, which it doesn't matter what your working directory is, that points to the exact location of something. So here's the absolute path, home Dinsdale memo.txt. All right, you can do list_dir to see the files that are in there. So we're looking at that directory called photos, which is a relative path of the current working directory. And you see there's these objects in there. Here it doesn't tell you whether they're files or folders. There's a text file named notes.txt and 3 directories. And you can also look inside the subfolder. This is photos/Jan 2023. It shows you what's inside there is a few photos. You can see if a path exists, photos exists, but photos of April does not exist because it only had January, February, and March. You can see whether a path refers to a file or directory with is_dir. So photos is a directory and is file will tell you that this is a file. So you can do that to tell files from folders. All right. They mentioned, by the way, of course, that Unix uses a / and Windows uses a /. So if you want to write code that will run on both Windows and Linux, you could use this path join command to attach the pieces together in a way that will match whatever operating system you're on. So this should also work in Windows by putting in backslashes. So that's probably useful. Now the next thing is formatting numbers. You can define a number of years as 1.5, number of camels you saw as 23, supposing you're counting camels. And now you could write that to a file. You could just write the number of years and write the number of camels. It's just as a string. But if you do that, then you've just got the 1.5 followed by 23 all rammed together, so it just looks like a long number. And this is not very useful. This is not storing the data in a way that you can get it back in a very meaningful way. So it would be better to put some text around it. You could say, I have spotted this many camels. This is the F format, where you can define a placeholder here. And you have Python expressions in curly braces. And so this will be the variable there. So fill it in, I've spotted 23 camels. Now we didn't specify the format of this number. So here we can say in number of years I've spotted that many camels, and there's something you could write that would be better than what we had. You can also contain operators and function calls, so I can multiply it by 12 and round it off to the nearest integer. And that'll give me 18 months I've spotted 23 camels. So you could write to a text file like this. You could use the F format to write years of observation, number of years, carriage returned, and camels spotted. And so then you'll have a more orderly output. It'll look like this. Okay, that's a lot better than just having the numbers run together. And you can also include other things like lists and directories in these curly brace things. So it's a really pretty handy way to output data of almost any type. If you put an invalid expression, T is a list. Now you could append another number to the list, but you can't just add 2 to the list because it's not an integer. So if you do that, you'll get a type error. Cannot concatenate int to list. All right, and another way to store things is YAML. Boy, I see this a lot in Linux environments. A lot of tools use YAML formatted data. So here I have a directory, photo directory, photos, data directory here, extensions there. This is just a list of keys and values, a dictionary that we've done before. And so if you want to write that into a file, you could use fstring, but there's a module called YAML that automatically formats it. So you install the PyYAML package, and now you import YAML, and now you do YAML dump to print out the dictionary. And it automatically formats it, and it formats it in this YAML format where you have a key value and key, and then multiple values and key value. So this indentation and the dash are part of the YAML format. And so it's more or less human readable, although spacing does matter and white space matters. But the cool thing is once you save it, you can read it back with safe load. So I can do a safe load and put it in something called config readback. And now this is config readback. So that's pretty nice in a structured format. Of course, there are other structured formats like JSON that would work too. But anyway, YAML seems to be the one they like in this chapter, and that's fine. A lot of people use it. By the way, notice we now have a thing called config readback that contains this data. And we had an earlier thing that we wrote here, config, that had the same data. So even though those two dictionaries contain the same data, they are not equal to each other. You can check because one was just created by reading it. We have two things that contain the same data, but they're separate objects. And then there's something called shelve, which is some way to write a database. I'm used to using SQL and MySQL, which are industry standard ways to write database. I haven't used shelves, but this is another way to do it. So you can use the config dictionary that we just talked about here that has these three objects, data directory, extensions, and photo directory. So we can look at, say, data directory, and there it is. So you can create this directory, create that thing called photo info, and then OS path join to make a path that includes the name of the shelf file we're going to call captions. And now we can use shelf open to open the shelf file. And C means it will create it if necessary. So now we have an object. This is just a pointer to an object. That's DB. And now the shelf object acts like a dictionary. You can set a value to keys or something. So we can have the name of this picture, cat nose, and then we can look up the key, the data, and then print the value. So the value is cat nose, and the key is this path to the file of a cat nose, presumably. And you can make another assignment to an existing key that will replace the old value. So if I change it to this, then it now has this number. It doesn't have two values tied to the key. It just replaces the value of the key. And so you can use keys to see the keys, of which there's only one. You can use values to see the values, of which there's only one. And you can use the in operator to see if a key appears in the shelf. And you can use a for statement to loop through the keys, for key in DB, just like you can with dictionaries. That'll print the contents of the dictionary. All right. And they say you should close the database when you're done, although when you exit a script, it automatically closes the objects. All right. So if you list the contents of the data directory, you'll see two files, and we can take a look here. It's photo info, right? Yep, and I only see captions. Now they say sometimes you'll see a backup file. And I think if you run this notebook more than once, you might see that file left behind. Apparently that didn't happen to me here, but it could have. So that's why they added this, to remove that backup, just to be consistent, I think, with the print copy of the book. Not that it really matters. And now you can look at the captions.db, which is the contents of that directory, just this one file. Now, captions.dat contains the data we just stored. Oh, I see. Well, I don't see two files. That's why I think something is a little messed up here. Yeah, all I see is captions.db. I don't see this captions.dat or anything, so I'm not quite sure what that's about. Anyway, and you can also store more complicated things than strings in there. So here we made a dictionary that had a map from a sorted string of letters to a list of words that can be spelled from this letter. So if you have these letters, you can make many words out of it. So this is going to sort the letters in a word. I'll just return a string which takes the letters and puts them in order and puts them back in a string. So if you call it on POTS, it will return OPST, which is alphabetical. The letters in an alphabetical order. So now you can open a shelf called anagram map, and then we can add an item to it like this. So the key is a string, and the value is a list of strings. And the word was defined up here. So we're going to add this word POTS to it, tied to that. And so now the value of that key, which is OPST, is a list containing only one item, POTS. So you can now add more. You can set key equals sort word of word, and there's the key, and the word is tops. So that's going to be another word and another with the same key. And so now if we append the word, you would think this would work for a list. But you could append to the list inside there, but this DB key, I'm actually surprised this doesn't work because DB key is a list. So let me try this. If I print DB key alone, I just want to do this to try to understand this better. I thought I had it when I went through this earlier, but now I'm not convinced. All right, there's DB key, and let's do type of DB key. There. So DB key is POTS, and it's a list. Therefore, you should be able to append something to it. And why do they think that is incorrect? Let's print DB key again after doing this. All right. And it's still POTS, which is actually kind of strange. All right, it looks like it has not been updated. I agree. Here's the problem. When we look up the key, we get a list of strings. But if we modified a list of strings, it does not affect the shelf. Oh. So DB key is a separate object, and adding something to that somehow doesn't get back to the shelf. That's interesting. Okay, So this is like a temporary local copy of one record you're modifying, but you're not getting back in. In order to do that, you'll have to create a new shelf. So you have to get the list, add the word, and then put it back in. Okay, that's interesting. That's not obvious at all. Now we'll have both values in there. Okay. All right. And anyway, what they wanted to do here was find duplicate files, a fairly common problem people have to do for various reasons. And one way that you could do it is by comparing the files, the entire contents of the file. So you could, if you want to compare images, you'd read them in binary mode, and then you'd take in all the data. So this is going to be a path to a binary image. This is going to open it, and this is going to read the whole thing. And then you can print out the type of data is there. And if I print, let's see what happens if I try to print data 1. It's probably pretty big among other things. And it's binary data, so it's probably going to make a mess. Yep, that's what you get. You get this garbage, which shows you every hexadecimal byte. By the way, JPEGs always start with FFD8. That's the marker at the start of a JPEG, and the marker at the end is FFD9. I know that from forensics and file carving, so that's what it is. That's the raw hexadecimal contents of a JPEG. All right, that's what's in there, that data 1. So now you have a bytes object, a long sequence of bytes, so you could read a second file, put it in data 2, and then see if they're equal. That is one possible way to compare two images. You can see it's pretty clumsy. You have to hold all the length of the image in memory and then compare the whole thing. It's arguably very precise, but there is a simpler, better way, and this is a hash value. So here they're doing it this way, though. And if you have two files, you can do it that way. But nobody does this because that's why we have hash functions. There are hash functions like MD5 that have very few collisions. A collision is when two different files hash to the same value. And while it is possible for MD5 to have that happen, it's not common. So what you can do is calculate the MD5 hash, and the MD5 hash is only 128 bits long. So it's a way to put a fingerprint on a file. And if you use a more modern hash like SHA-256, there are no known collisions of that, so you have 100% confidence that if two files have the same hash, they're identical all the way through. MD5, it's pretty likely too, but it's not quite as accurate. So this calculates the MD5, this defines the MD5 hash, and you can do the update method to add data. So I can update it with data 1 and then print the hex digest, and you get this relatively short hash value, and that's enough. That's a fingerprint that tells you what's in the file, and any file with the same contents will have the same hash, and any file with different contents will have a different hash. So you can put all that in a function, and now you can compare the hash of image 2, and you can see this one is AA1, this one is 6A5, so the files are not identical. If they were identical, the hash would match. If they were different by even 1 bit, the hash would be totally different. All right, so you can now search through a directory. This is what you do if you want to find all the duplicate files. You'd search through all the directories and all the subdirectories, find all the files, calculate all the hashes, and then see if there are duplicates among the hashes. That's an efficient way to do that job. Here's a way to walk through the directory. So you can walk through, and it shows you all the photos. So this gives you a relative paths from where we are to every photo and every file, and you could then calculate the hash values and compare them here to find duplicate files. All right, and this is kind of useful. It's fairly common, especially in using Unix systems, that you have white space and unprintable characters in something and you can't find them. Like this is 1 space 2 tab 3 carriage return 4. So when you print it, you get a mess like this, and you might want to get rid of all that white space to clean it up. So this function, which is pretty cute, repr will print with the representation. \T for tab, \N for new line. So that will help you find out strange white space in your files. That might be useful. And another issue they talk about is capitalization. In Mac OS and Unix, capitalization matters. So a file in capital letters in the name is different than the same file in lowercase letters, but not in Windows, which confuses people. Anyway, that's what I wanted to show you there. I'll stop this video.